short, if everybody agrees on in this part of talk. And also Max suggested the difficulties with the larger particles collection and the wind tunnel study. So our last speaker of this afternoon, she will exactly talk about these experiments in with Icelandic and other dust. But at the moment, I will check the chat if there are any questions.
Carlos has raised his hand.
Yes, so Carlos, please. You have to unmute yourself.
I was wondering, well, I mean, I think Max, you should write a paper on those data sets. So that's very cool. And I would like to know the AQ watt. What is the difference with the FIDAS?
Well, actually, first of all, you're invited to write a paper. You have no time to write papers. You're a business guy.
No time.
And well, we can use the sizes or perhaps write something together with your data and our data. So the difference is actually it's exactly the same sensor. Yeah, it's exactly the same sensor. We have a different volume flow of only 1 liter a minute. It's just a new development after 10 years of the feeders in the market. And it's smarter, it's cheaper. Well, it's not certified for certified monitoring according to the European guidelines, but data quality is well, it has the same data quality as you have with the feeders. Yeah. What we have not done yet is to really measure how large particles, how it behaves for very large particles in comparison to the feeders. That's what we not have done yet, because the one is smaller, the sample is smaller, so we don't know that yet, but we are going to measure that. Yeah. But it has also 256 raw data channels, and yeah.
Okay. So just letting you know, in Iceland, we did a final test and experiment in the end of the campaign. I didn't mention this.
Yeah.
We replaced the, because there we are measuring we're measuring under high wind conditions where, you know, for dust emission, right? So we also tested in parallel the 2 feeders, one with the head that you have, Palas, and one with a directional inlet. We're analyzing those data and we'll let you know for comment. So that would be interesting to have your feedback on that. And then my last question is the cloud monitor. Do you think that's something we could use to measure dust?
Well, yes, the cloud monitor has a much larger measurement volume. You may know the feeders is only analyzing a small portion of the total volume flow. The cloud monitor has about a factor of 20 higher statistics, yeah, and it has a very large measurement volume. So the total volume for 5 feeders is analyzed, and we have some running now. David Ross now, Bruce is using one, and we have one running in USA, and the climate channel, by the way, of KIT of Manila, the Pine system is using.
Yeah.
And in general, that of course, due to the larger measurement volume, the better instrument, because you can make really much better statistics than you have with the feeders. Yeah, and it has a heated inlet, by the way, also a heated inlet to measure at very, very extreme conditions, or if you have super cool water, something like that. So you have no icing on the inlet. Yeah.
Cool. Thank you.
Yeah.
Okay, so thank you everybody for the question and for the talk. So now we will move to our second speaker of this section, and that's Alexander Böhmländer, if I spell it correctly, from the Karlsruhe Institute of Technology, and he will talk about a mobile filter-based sampler to measure the ice nucleating particle concentration on an unnamed aerial vehicle in the Arctic. So please, you can come here. It's an on-site presentation, so we will share the screen from here. And just prepare it here for you. We're not stuck. Yeah, we are this one, right?
Yeah, so hello everyone. And as Pavla already said, I'm going to talk about ice-nucleating particles more at the moment. And Max already mentioned the pine chamber, for example, where we measure ice-nucleating particles. And my setup is basically the different way to measure ice-nucleating particles by just collecting them on a filter and analyzing them back at the lab. So on the right, you can just see like a typical screen that you sometimes see with the emissions on the ground. And then we have, for example, aircraft-based measurements or ground-based measurements. And usually it's hard to link these, or you use remote sensing for aerosol optical thickness or something similar. But another way to measure directly below the cloud or directly above the cloud is by using balloon-borne or UAV measurements. And this is what I'm going to talk about today. So the importance of ice-nucleating particles in the Arctic is quite equivalent here. So you have, of course, super cool liquid cloud droplets, and they can nucleate above -38 degrees Celsius in the presence of INPs. Then, of course, there is a high precipitation coming just from the ice phase of these clouds. The phase of the cloud, of course, also has a dependence on their radiative properties, and also just in general, due to Arctic climate change or Arctic amplification at the moment, these mixed phase clouds have a huge contribution to that. And the inclusion of ice-nucleating particles, INPs, is needed to accurately reflect this change, especially since the Arctic has been warming more rapidly than anywhere else on the planet. And for this specific measurement platform, it's needed to motivate why we need vertical measurements, especially in the Arctic. So at the moment, aerosol cloud interactions, so INPs and also CCN, cloud condensation droplets, how they work is severely understudied in the Arctic. And also because the Arctic has a very stratified atmosphere, you need to compare ground-based measurements to the actual measurements on cloud height, for example. And so therefore it's a question how reliable measurements on the ground are for the actual clouds in the air. And for example, there was one study from, I think, 2 years ago, where they measured particles, aerosol concentrations in the lower Arctic atmosphere in Alaska, and they saw that only 14% of the measurements were actually representative of the ones that they had on the ground. That is, of course, depending on where you are location-wise and also on the weather and ambient conditions. But it's one point that is important to measure more vertically resolved in the Arctic, especially to collect more data in different locations, different seasons, to assess the actual influence of the INPs in the Arctic. So here again, this typical graph where you have the aircraft-based measurements in the top, where you can go into ice clouds, for example. Then you have the ground-based measurements where you usually have the emissions coming from, so for example, Icelandic dust. And in the middle, kind of the UAV, where you can go up to 2,000 meters in height and assess the vertical resolved measurements. And the big point of UAVs is that it has a quite high flexibility in comparison to aircraft measurements that have to be planned in advance, and you have flight paths developed for these. And also, of course, you have a much lower cost compared to aircraft measurements. Just one aircraft measurement is much more expensive than just buying one UAV and buying one sampler for that UAV and flying it. Then, of course, you have the added mobility of like using different setups on your UAV. So you can buy one UAV with a hull that can fit multiple measurements or instruments, and you can just interchange them depending on your conditions or what you want to measure. Of course, you have the problem that you always need an operator. So you need someone who actually knows how to fly a UAV, and they have to watch the UAV during the flights. And also, of course, compared to an aircraft, you can't have a lot of weight. You don't have a lot of space. And especially in urban regions, it's very hard to measure or because of restrictions. But in remote areas such as northern Finland, for example, or I think also Iceland, it's probably much easier to get permission to fly UAVs. So here you can see our flight platform that we are using. It's just a styrofoam hull. And you can see here under the wing is the filter. It's at the moment closed. And you can also see like here you have the airspeed sensor for the UAV and a small ambient sensor just to give a direction on the temperature, the relative humidity, the pressure that we see during the flights to see if the ambient condition changes during each flight. And this type of flight platform has a total flying weight of 2.5 kilograms. So that means roughly 1.2 to 1.5 kilograms of additional instruments that we can put on the UAV to measure. And also it has quite a large space where you can place your instruments. So for example, we are mainly using a pump and a flow meter. And this type of airframe also enables you to measure up to 2 hours. So we can filter at one height for extended amounts of time to actually collect enough INPs to actually analyze them in the end, because INPs are very rare compared to general aerosols. And therefore, this UAV is actually very ideal for filter-based sampling because you have long flight times at one height. And here you can see just a typical sampler for us. So on the left here, you have the nose of the UAV, then you have the aerosol coming into the filter, then it goes over a flow meter into a pump. So we measure the flow during the whole time of the flight. And this micro diaphragm pump provides a flow of roughly 15 liters per minute at standard conditions. Of course, the higher you go, you get lower flows. But since we have this flow meter and that measures the mass flow, we are always the same. Essentially, we are not dependent on the pressure there. And this filter is polypropylene, and it's soldered with a nuclear pore filter, which has a diameter of 47 millimeters. And as you saw before, we have additional sensors on there to monitor the ambient conditions. And also all of these instruments are read out by one single Raspberry Pi, but of course you can use whatever little microcontroller you want to use, like an Arduino, for example. And to verify that our setup actually works and collects the right data, we have a similar setup that is placed on the ground and then compared to ground-based measurement stations that are there. So the total flying or the total weight of our setup is 870 grams roughly. And our limit of INP detection is roughly 2 times 10 to the minus 3 INPs per standard liter. And here you can see a typical flight path of our measurements. So this is in northern Finland in cooperation with the FMI and also with David Bruce. So yeah, this is in northern Finland. It's one space where you have no forest essentially, so you can easily fly and start and land there. And yeah, you can see quite clearly it starts here. We just throw it essentially by hand. And then it climbs to the altitude. It circles there for 1.5 hours up to 2 hours. Then it comes down, we collect the filter, and that's basically a typical flight. So at the beginning, the filter holder is just loaded with a nuclear pore filter. And that's where you saw the picture earlier, which is still closed. We have no INP sampling there. Then we start all the measurement systems with the Raspberry Pi, start the controller for the UAV systems, and check if everything is going well. And then we finally remove the clogging from the inlet, and then we start it, and it climbs to its destined height. And after the flight, we collect the nuclear pore filters for analysis back in the lab. And one point that is especially important for INP measurements is that you have to recognize that during handling, you can contaminate the filters. So what we always do during these campaigns, we collect a handling blank, which is just, we do the same procedure as usual, we just don't turn the pump on. So it's just a filter which shows the contamination from the handling. And the past measurements we have done 3 field campaigns in Pallas in northern Finland in cooperation with the FMI. And the first campaign that we did was in autumn 2020, where we first tested the setup of the nuclear pore filters on the UAV. And what that showed was that we have a quite clear distinction between the blank filter, so the handling blank, and what we actually measure. So that essentially shows you the proof of the concept that you can see here quite clearly. So this is just a frozen fraction over the temperature. And you can see in blue and green, this is just the water background that we have from our instrument. So that is the water that you wash the filters with. And then in orange, you can see this is the handling blank that we see. So that is very close to the water background that we have. And then we have one filter that we have actually flown with an active airflow on the UV. And you can see here quite a spread of a few Kelvin where they are not the same, essentially. And then last spring, so almost 1 year ago, we did a campaign at the same location where we just refined our setup further. We changed it a little bit, the flow path. And essentially what you can see here on the left is just the IMP concentration over the temperature. And here in blue is the UV filter, and in orange, the ground-based sampler filter. And you can see here they're actually very well aligned. So they are essentially the same for here. They have the same nucleation temperatures, the same range, and also the same IMP concentration for the whole range, essentially. And 1 day later, on the 21st of April, what you can see here that it quite changes a little bit. It's not super pronounced, but you see here that there's quite a higher concentration of IMPs for higher temperatures here already. And especially for the UV, they start later, and there's also different shape. But of course, at the moment, these are just measurements of how the system works and how the UV behaves during flights. And we need to do more measurements with this system to actually get a higher statistic on these, on that different ambient conditions in different locations. So therefore, coming to the conclusion and the outlook, this setup was tested during 3 field campaigns in Pallas in northern Finland. We have flown it up to 1.4 kilometers in height. And usually flights go at least 60 minutes, depending on the wind speed, of course, and depending on where you want to go at the altitude. So if you want to go higher, you need more battery power, essentially, to actually fly the same amount of time. And in the future, we are planning to couple it with an optical particle detector, essentially under the other wing, which will be an open path optical particle counter to also get the aerosol size distributions. And also in the future, we will use this setup at the Willem Research Station in northern Greenland this summer, in cooperation with Julia Schmale from the EPFL, where they will fly the helikite with our payload. And we will also use the Skywalker UAV as additional measurements, so we can compare how the measurements look like on the ground compared to balloon-borne and UAV-borne sampling. And additionally, we also have bought recently an octocopter that will fly fast height-resolved measurements, which is also equipped with a feeder's fly from Pallas, which we will then use to assess the situation to see at which altitude we want to fly with our UV to measure IMPs. And now just two pictures from the campaign in last spring. So on the left, you can see the two Skywalkers circling in front of the moon. Quite nice weather. I wasn't there, but I would have loved to be. Yeah, and on the right, it's just a frozen sea where we start and land the UVs during winter or during springtime. And you can see the UV here in the front and telemetry, and that's all you need for UV-based measurements. That's quite not very complicated. And for that, I'm done. Thank you very much.
Thank you very much for this great talk. And yeah, you have amazing plans for the future. So good luck in this high latitude. And does anybody have question here? So nothing on site.
How much wind can you operate it in?
10 meters per second is the usual limit where we have. It depends also on the gusts. So if the gusts are strong, but an all wind is fine, then it's hard to measure. But 10 meters per second was the highest that we've flown.
All right, so there are no, yeah, for Iceland, dust storm.
That's fine.
So, and now I would like to welcome our last speaker of this section, and it's from west part of Canada. So it's gonna be Dr. Tamar Richards Thomas, and Tamar has done amazing experiment with high latitude dust in wind tunnel and other different experiments. So, Tamar, are you there?
Yes, I am here.
Welcome. So the floor is yours.
All right, thank you. Hi, everyone. I'm just going to share my screen here, and you can let me know if you're unable to see it.
Yes, we see it in full mode.
All right, perfect. So hi, everyone. As you are aware, my name is Tamar Richards Thomas, and today I will be presenting on my study that I completed during my doctorate program. And so I worked specifically in Trent Environmental Wind Tunnel at Trent University. And so I will be sharing some of the key findings that we have gathered through a number of sections of the study. But before I begin, I would just like to say thanks again to everyone who had contributed meaningfully and significantly towards this project. I mean, it wouldn't have been possible without you. So without any further ado, I will get right into the presentation. So the main goal or objective of the study was to understand and assess Icelandic dust entrainment, emission, and deposition. But this time it's completely through a laboratory study. As a result of that, it was divided into 3 parts. In the first part, we used different technologies to understand the characteristics of Icelandic dust particles in comparison to those of solid spheres. And in part 2, we worked in the wind tunnel to understand the effects of wind gusts on dust emission. And in part 3, we use a 2-dimensional laser Doppler anemometer to measure the settling velocities of Icelandic dust particles, as with a strong focus on the particle characteristics and climatic conditions. And so there are publications or associated publications for each part of this study. There was also a part 4 of this study, but it's still in development. And once that becomes available, of course, with all opportunities, I will be sharing it. So the samples were collected in various locations in Iceland, and there were 5 samples. The sample sites were located within and near severe erosion regions. And it is important to note that there were experienced field researchers who collected these samples. They are listed on this slide. And as a result of that, careful thought and considerations were used to collect and to determine the field site locations. So the samples collected are pure volcanic ash, called ash, from the 2010 Eyjafjallajökull volcanic eruption, glaciogenic sediments, Glacier 1 collected in the northeast region, Glacier 2 and 3 collected in the southern regions, and an unknown mixture of ash and glaciogenic sediments we refer to are called mixed. And so those were the 5 samples. But it's also important to note that in each part of the study, we use varied textures of these sediments. And so as I go along, I will be providing you with more details about that. So as you are aware, we had the 2010 Eyjafjallajökull volcano, and when it erupted, it caused large-scale flooding that created outwash plains, such as the one that is shown in this slide. But a close-up observation of the surface of the particles show us that they are highly angular, and much of the speculation was also similar to that. But a closer observation of the surface even showed us that they are indeed angular. They contain flaky dust coats, they are porous, and they are rough. But the problem is that models, or should I say atmospheric dust models, typically assume that these particles are spherical in shape. And so how can we compare Icelandic dust particles to those of solid spheres? Well, what we did was to measure the bed surface areas to get some understanding of the surface roughness of these Icelandic particles in comparison to manufactured solid glass spheres. And so the results are shown in figure A. What we can see is that the measured bed surface areas increase or is larger for all Icelandic samples in comparison to that of the solid sphere. We went further to calculate the geometric surface areas, and we plotted that against the measured bed surface areas. And what we could have seen here is that the calculated geometric surface areas greatly underestimate the measured bed surface areas for all Icelandic samples. But the dashed line that you're seeing in figure B shows us the 1-to-1 ratio. And indeed, as expected, the glass spheres showed a good agreement between the calculated and the measured bed surface areas. And so this is an image that shows what the glass spheres look like, and they are manufactured glass spheres. So moving along here, another at the time, so I'm not too familiar with what happens now in the literature, but at the time, the porosity of these particles had never been measured, even though, again, there were lots of speculation as to the fact that these particles were porous that contributed to their light weight. And it could have been because it's a very expensive process when we figured it out, and it was also time consuming, but nonetheless, we were able to look at the pore size distributions for 3 of the 5 Icelandic samples. And these are the pore size between and within the particles. And so what we found was that for the particle size distributions that are similar, we obtained pore size distributions that were also similar. But as the pore sizes increases, it increased for larger particles that were contained in Glacier 2. But overall, what we can see is that majority of the pores were within the macropore size regions, so they were large. And these are the pores between and within the particles. So in Iceland, we know that wind gusts can be up to even 50 meters per second, and up to about 3,000 tons of dust could be released in a single event. And the problem is that the effects of wind gusts on dust emissions are not well understood. And so in part 2 of this study, we use the Trent Environmental Wind Tunnel to understand the effects of wind gusts on Icelandic dust emission. So in this slide, what we can see on the right side of it is a schematic diagram of the wind tunnel setup. And each run or experiment was performed over a 5-minute duration with wind gusts up to about 8 meters per second. That's the free stream. And at 10 seconds time intervals. The environmental conditions were obtained by an in-house climate control system, And as a result of that, we were able to keep both relative humidity and temperature at a fairly constant value, with a low relative humidity of about 20% and temperature around 19 degrees C. All 5 Icelandic samples were used in these experiments, in addition to a reference sample, which is mine tailings. Mine tailings were used because the porosity and the bed surface areas were very similar to those of what we were obtaining for the solid glass spheres. And as a result of that, it served as a good substitute. And in addition to that, it was easy to source and very inexpensive in comparison to the solid spheres. So let us take a look at the results here. Here, what we can see is the temporal response of the dust concentration, and that is as it relates to wind gust speed that are typical for all samples, with the exception, of course, that the magnitude of the PM10 concentrations were different for different samples. What the figure here shows us is that we can see distinct peak concentrations or PM10 concentrations for each velocity stage, and that is upon threshold. So as the velocity increases, we see these distinct peak concentrations. And this pattern was fairly similar for the samples that we had worked with. A further calculation or analysis of the dust concentration led us to look at the logarithmic plot of the PM10 emission rate plotted against the friction velocity. And so what we can see is that the emission rates are higher for the samples that contain coarse sediments than for those that contain more fines, meaning they contain less sand-sized particles. And in figure B, what we can see is an extended plot again, but in this case, we have looked at the vertical dust flux. The equations are not shown, and that vertical dust flux is plotted against the emission rate. The dashed line shows us a one-to-one relationship. And what you can see, they show really, really good agreement for all the samples, except at very low values or calculated values of the vertical flux. We can see the vertical dust flux underestimating the emission rate. But overall, it showed really good agreement for all samples. We further compared the vertical dust fluxes for relevant field and laboratory studies with those obtained in the laboratory wind tunnel study of Ore experiments. And what we found was that there were good agreement between these data sets, more specifically the magnitude of the vertical dust flux from our experiments were actually within similar ranges of those that were measured in other high latitude regions and field studies, and also for other volcanoclastic dust samples. So the takeaway message from this part of my study is that we need coarser sediments, or in general, coarser sediments. They essentially influences the dust emission rates. And as a result of that, we'll find an increased emission rate once these sediments tend to contain more coarse particles. Now, when the 2010 Eyjafjallajökull Euclid volcano erupted, it ejected a lot of fine grained sediments into the atmosphere. And as we can see here, the plume tend to spread in the southeast direction, whereas the resuspended portion towards the southwest. But the thing is that a lot of the models had assumed that these particles are solid sphere. And so the complexity of the particle morphologies, they cause many uncertainties in the model data sets that were produced. And this then highlighted the need for measured data sets from laboratory studies. So in part 3 of my study here, we used 4 of the 5 Icelandic samples in addition to the solid glass spheres. They were all wet sieved, and the purpose of that is to isolate the fine particles. So we wanted to use the finer stuff that could be transported over long distances. And as you can see here in the particle size distribution, over 80% of the samples contained particle diameters that were less than and equal to 50 microns in size. These samples were further exposed to varied relative humidity conditions to understand the effects of moisture adsorption. And the plot that we're looking at here shows us the equilibrium moisture content plotted against the absolute metric potential, which is the inverse of the relative humidity. For instance, if the sample would become fully saturated, what we'd find is that the relative humidity increases to 100%, but the absolute metric potential would decrease to 0. So based on what we're seeing in the figure, we can say that the equilibrium moisture content increases in the same order as their bed surface areas, suggesting that the larger the adsorptive surface area, the more moisture these particles may be able to store. In part 3 of this study, much of what we did was to measure the settling rates of Icelandic dust particles. And that was done in a sealed fall column. A 2-dimensional laser Doppler anemometer with a minimum particle detection limit of about 0.4 microns was used to measure the settling velocities of the particles. And as I mentioned before, in 2 dimensions, so that's horizontally and vertically. Both the sample and the setup were left overnight in preset climatic conditions. These, climatic conditions were obtained from the same in-house climate control system. But in this case, we used temperatures around 14 degrees C, which were similar or close enough to the average Icelandic summer temperatures, and relative humidity of ranges 20 to 30, 50 to 60, and 70 to 80%. Each experiment was conducted for up to about 30 minutes duration with the same sample, and measurements for each sample was obtained for, like, the number of runs that were conducted were over 10 for each sample. So as I mentioned before, the sample, the setup, they were left overnight in preset climatic conditions, and this enabled everything to equilibrate for experiments that were performed the following day. So the particles would be dispersed inside the sealed container, and so where the beams intersect at the center of that sealed container is where the velocities were measured. But in addition to that, adhesive tape on SEM stubs were also positioned at the base of the tunnel for a few minutes of the fall column experiments, just to collect some of the aggregate deposits during a few experiments to see what they look like. And so when we sent them back to the lab to image these particles, this was what they look like. And what we can see here, that at low relative humidity, the aggregate deposits were actually very complex. In the figures here, we could see the velocity distributions, and the velocity distributions were obtained from the lump data that were obtained over the 30-minute durations, and they are not time dependent. So the vertical velocities, they were similar for the samples that had similar particle size distribution. But the vertical velocity increases for larger particles that were found within Glacier 2. However, that is not the case for the horizontal velocities. One of the other things that we found was that there was a 9% density difference between a solid spherical basaltic particle and a porous basaltic particle, which show that that value is very small. And as a result of that, the weight of the particles is not as significantly different as it relates to a sphere versus a porous particle of the same size. And as a result of that, it may not be sufficient to affect the inertial and also the settling rates as it relates to the vertical components. All right, so just to summarize some of the key findings based on what I have talked about in this presentation is that in part 1, we had found that these particles are indeed angular. They have tons of dust coatings on them, and as a result, and they are porous, and as a result of that, they may be able to transport over very long distances. Water adsorption on the particle surface and within their pores may affect the rate of particle deposition through the growth of water films and lens, but also the particle interaction may lead to aggregation. Who knows how it affects cloud condensation, precipitation, and even solar radiation. And in part 2 of the study, we could have seen that the coarse sediments, they are most emissive in comparison to the sediments that contain less sand. And so the wind tunnel study that we had carried out showed really good agreement with studies that were actually performed in other field studies and laboratory studies. And as a result of that, that provide a much greater credibility for the measured results. And in part 3 of the study, the particle characteristics, they appear to increase the horizontal velocity, but it wasn't significant as it relates to the vertical velocity. And note that this is also at low relative humidity. The amount of moisture, though, that is absorbed by the dust particles, they appear to be dependent on the particle characteristics, and that may also enhance aggregation and influence the fall velocities. And so this is the end of my presentation. I just want to thank everyone for listening. And if you have any questions, I am welcome to take them. Thank you.
Are there any questions here on site? I don't see there any, so let me check the chat, or if there, yeah, Carlos has a, please go on, Carlos.
Yeah, thank you. Tamar, this is amazing work. Congratulations. So I have a question, 2 questions. One is on the wind tunnel. You mentioned that you have like more, I mean, you say it's more emissive for coarser soils in terms of mass, right? Okay.
Yes.
And when you refer to coarser sediments, what do you refer to? So, I mean, like, in other words, did you, I mean, in the wind tunnel, were you reproducing, you know, that did you have like did you have like both aerodynamic entrainment and saltation and sandblasting? Could you talk a little bit about that? And, you know, what do you refer to coarse? You mean like more sand particles that are, you know, like creating more dust because of sandblasting, or you refer to direct aerodynamic entrainment and, you know, coarser particles directly emitted in your wind tunnel?
All right, so yeah, that is a great question. So what happened, I'll explain what happened first, and then I'll explain as it relates to your question. So we were using relatively low free stream velocities. So the ranges were like from about 4 to 8 meters per second. And as a result of that, that led to a very shallow boundary layer, and hence the turbulence, it just wasn't, the turbulent length scale just wasn't long enough. And so what we found was that when we decided, okay, we're going to collect, you know, the sand that was saltating along the surface, it was just not sufficient to be measured because of, you know, the fact that we had a very shallow boundary layer. So when I refer to the sand as in, you know, the coarser particles, I was referring to those that were actually larger than, you know, that 63 micron size or around there. And but it was just not enough for us to really quantify to lead to an explanation for the saltation. The reason why we did that is because two things. We have the circulation, the background flow. And so it was so high, the dust concentration that we were getting off the surface with just that small quantity of sand that were, you know, causing the emission of dust. It was kind of just so high in the sense that it also led to, at times, the dust traps being broken. So in order to ensure that we could cover an entire experiment, we decided, you know, to stay within a certain limit just to make sure we can actually do the measurements. But if I was supposed to do this again, we'd have to find some way in which we can scale it to see what really happens with the saltation part of it. And actually, we had also thought about imaging. Like instead of measuring so close to the surface, further off the surface, because we were way far ahead, away from the bed, but we still measured quite a bit. So measuring, you know, further off the bed and using images to quantify that. So there are opportunities to look into that, but a very good question. We actually weren't getting enough sand to measure or to look into the saltation of it because we decided not to break the dust tracks and to ensure that we could actually get some measurements.
Okay, and the last question, just for segmentation, did you see, from your experiments, which are, by the way, very interesting in general, not only for high latitude dust, there's a lot of uncertainty in the segmentation rates of coarse particles in the literature and a lot of discussion. So what are the limitations? What are the limitations of your setup in the lab? And did you compare the segmentation rates depending on the particle size to theoretical, theoretically calculated rates? And was there a mismatch, as claimed in the literature, as being beyond like this kind of more like Stokes regime? So did you compare that to theoretical curves of sedimentation, like gravitational settling?
For the wind tunnel?
Well, no, you set up on the sedimentation, like the settling of the particles.
Oh, the settling of the particles. If I had
velocity, like to sedimentation.
So yes, we did. We also, I didn't present that part of it, but we also look at the drag coefficient. It's in the paper. And it was found to be in good agreement with what the theory suggests. But there are limitations with the experiment, and I will also explain that, in the sense that with the LDA, it only measures the velocities in two-dimensional, so horizontally and vertically. It doesn't provide you any measurement with particle sizes. So with that said, what we did was to measure these samples with the Ariba before and after the experiments, just a confirmation to see how much we have lost. But in terms of the velocity measurement, we used the same sample over and over and over and did a number of replicates so that if we were able to, like we've done with the distribution measurements, we had several data set that we could put together to understand what that distribution looks like. But a confirmation through doing the particle size measurements before and after showed that we didn't lose a lot of the sample throughout those measurements. And as a result of that, what we did was then to look at the median size that we have, that median 50% size, and also velocity. And that was when those are the measurements that we use from each sample to calculate the drag coefficient. And that's when we got a really good confirmation that they were within what was expected. But otherwise, we could not do it outside of that because of the limitation of not knowing which particle size directly provided us with this velocity measurement. So that was a big limitation. And yeah.
Thanks a lot. So I'm going to leave the floor to others. Thank you.
Welcome.
Thank you very much. So this was the last talk of this session. Thank you very much, everybody, once again.
Right. Thank you for having me.
And Tamar, I would like to ask you to stop sharing your screen, and if you online presenters would be so, or is there one more question from you? Is it? No, anyway, if you could turn on the cameras and we would take like one picture or so of the online attendees just to have it. Thank you.
Oh, should I share my screen again?
No, if you, all of you who are today together with us, if you could turn on the camera and I will take a print screen. Thank you. Just a second. Also with us here. No, but how do I gallery view? Yeah. That's exactly. It's always nice to. Yeah, okay. Some of you don't have the camera. Great. Now we have to turn. It's almost there. Just a second. Maybe Adolfo. And Sikana Basi also. Great. So yeah. Thank you, Nichko. And maybe Sylvia, Adolfo, and Jim. And I can take the print screen. Well, shall I turn my camera on too? I haven't realized. Okay. So, yeah, I take it. Okay, thank you very much. And yeah, since the time is a little bit later, I believe that that we will just meet again tomorrow at 1 o'clock. And there will be another really exciting presentations prepared tomorrow. So have a nice afternoon and evening, and thank you for participating. Goodbye.
Bye.
Just save the print screen is the most important. No, it's, yeah, okay, we have it saved. Yeah, it's always hard. Sorry for this. Okay, now I mute. Number one is to mute and stop recording.